If you just arrived, don't worry, you haven't missed anything important. We're just getting started. And the big word that we're going to discuss is scalability. So people have been talking about scalability quite a lot in the last few years. So everyone says cloud, but generally they mean horizontal scalability. So just let's throw more machines at whatever problem we're trying to solve, no matter what the networking costs are, what the bandwidth will be, and like how slow the communication over the network can be itself. So today I'm not going to touch this. So distributed computing is one of the few things that will bypass and will cover a lot of other stuff. So when we start implementing whatever idea we have in Python, we generally have a baseline implementation that is not probably that fast, but it gets the work done. So I've marked it with a snail. Us, at least at Uno, we often want to go forward with faster implementations once we have the baseline defined. So the very first thing that you can do is re-implement that same thing in C or C++ in a compiled language and get, let's say, a 40x performance improvement over your baseline, even in a single-threaded application sometimes, which is remarkable. Another big form of acceleration is, or let's say vertical scaling, is enabling application-specific accelerators, or let's say purpose-specific accelerators like GPUs, that we so often have in our modern servers. But those things you may have heard before. So there is an ambition to process data faster. In the case of the CPU or native code, this would also imply lower latency. In case of GPU processing, we generally imply higher bandwidth. The latency may not always be that good. But then there is another set of challenges. So essentially, the baseline is Python. One form of advancing your original baseline implementation is designing, let's say, a parallel or native solution, which is the second row, making it work faster, whatever it means. And the third row is making it bigger. So like, how can you make it work with data sets that do not fit into random access memory? That's another very challenging thing. And hopefully, there is a holy grail at the very end. Once those two worlds meet, working with data sets that do not fit into random access memory and doing it real fast. So today, as the first talk of the conference, I really want to give you hope that this last step is possible. And our ecosystem is maturing for you to have all those cool data science tools without actually having to rewrite much of your Python code. And frankly, if there's like a 500x difference between your baseline implementation and whatever you can get by changing just a single line in your source code, why not use it? So when you buy a hardware or like a gaming rig for yourself, you would spend thousands of dollars on a machine. But if you are using or running a code that is 500 times slower than whatever it could have been with just a single line change in your source code, then you're essentially boiling yourself down to Raspberry Pi Pico $4 board. While at the same time, you could have gotten 16-core, state-of-the-art AMD CPUs, and not just one, but 4 of them. So modern hardware deserves proper software, and we're going to give it to it. So just to get familiar, modern server would look like this. It's a 6.5 unit rack, mountable server. It will have tons of state-of-the-art SSDs. It will have 64-core CPUs in it and a ton of networking. But even when we start programming those machines, we would oftentimes start with libraries like NumPy, Pandas, and NetworkX. Raise your hands if NumPy sounds familiar, if Pandas sounds familiar, and NetworkX, have you ever used it? OK, far less. And it's the general trend. So as the data and the data form becomes less regular, it becomes more challenging to work with it. And we'll also see in the following implementations. So I've only briefly referencing some of the libraries that you can replace your original choice with to get a faster implementation. And many of those libraries would have a prefix Cu, which stands for CUDA, implying GPU acceleration. And I'm pretty sure in the next 2 days, you'll have a lot of guys explaining how this works under the hood. Aside from those, there are other attempts to implement native acceleration. So Modin would be an analogous project trying to give you native implementations of data frames. And it's pushed forward, not explicitly, by another big hardware vendor. Let's not call the names. But then there are some completely open source projects. So RetworkX has an R in the beginning. Who knows in which language RetworkX is implemented? C. Not too many options. C. I gave it away with R. Maybe Rust. Yes. OK, we have a winner here, Stefan. So I've also referenced some of the libraries that will give you horizontal scalability, like Dask, cuDF. But I told you we're not going to talk about distributed computing or computing over the network today. So what it could be? Well, distributed can mean a lot of things, such as having multiple machines working together or multiple chips working together. So Dask cuDF would allow you to also scale beyond one single GPU with data sets that do not fit into VRAM of a single chip. But OK, this conference is about Python and data processing, not C or CUDA and data processing. Well, I'm here to tell you that you will not have to write a single line of C to get this working. So it's just Python. To give it a slightly more structured form, let's classify them into tabular implementations, native versus GPU acceleration. And one interesting thing to note is I have question marks here. And NumPy is surprisingly in two categories. So we'll remember that question mark. And now we'll concentrate on the question how hard the transition can be for your sources in your application to become, let's say, 20, 30 times faster. So NumPy is a lie. And it's just a face. In reality, there's a lot of interesting stuff happening under the hood. So it gives you a very convenient form of working with matrices and higher ranked tensors. But in reality, there's like this standard defined, I think in 1979 or something like that, which is called BLAS, basically Linear Algebra subroutines. It is one of those standards that definitely aged well. It has 3 layers of operations: vector operations, vector matrix, and matrix-matrix operations. And oftentimes, or probably always, it's implemented in C, C++, or just native assembly, raw assembly. But originally, it was implemented in Fortran. So when I say it's a standard, one of the cool things for you to immediately grasp is that it do not really force a specific implementation. So you can have the same usable front as the NumPy gives to you. And under the hood, there will be a hardware-accelerated implementation that is completely detached from your original NumPy solution. And whenever you use pip install or conda install, it's just a question of adding a couple of specifications in square brackets right after your install declarations for you to instruct the underlying package manager which specific distribution of NumPy you want installed. So one of those to remember, and generally the one that I would recommend for you to start right away with, is Intel MKL. So MKL surprisingly has no B, L, A, or S in the abbreviation, which is very uncommon for BLAS libraries. Almost all of them have at least one of those 4 letters. But MKL stands for Math Kernels Library. It's a very big package that includes a BLAS distribution optimized for x86 CPUs. And note here, I'm saying x86, implying that it will work fine not just on Intel hardware, but also AMD CPUs. And last but not the least, there's CuPy. And whenever we want to talk about performance, it makes sense to describe what kind of benchmark we have. So we love doing benchmarks. Generally, they are pretty thorough. But like, to be honest, for this conference and talk, we wanted just to give you a basic understanding with some of the most common operations. So some of them would be more like linear algebra operations, like the one on the left in the middle on the slide. So like matrix multiplications, SVDs, fast Fourier transforms. Another ones would not even have native implementation in NumPy, such as like moving averages computation, which is at the very top. And the others will be like purely arithmetical and would include things such as reductions, median calculations. And when I say arithmetical, I imply that do not really take into account any of the structure that you provide with the input. So like, it doesn't matter if it's a matrix, ranked 3 times or whatever. For those functions, it's just like a continuous array. And you need to analyze all the numbers regardless of their position. So the cool thing here is, as if we have an interface and the underlying implementation can be abstracted away, you can have a lot of very custom, exotic hardware actually implementing the number crunching. And when I say exotic, I mean it. Like, this is the kind of chips that, even given all my pure love for hardware, I haven't worked myself with. But being in the industry for a few years, I have an expectation that once I get those chips, and I have the BLAS distribution that comes with it, I will be able to rebuild NumPy and link it together with a provided BLAS implementation, and my Python source code will work right out of the box on those chips. And to give you an understanding of how different those chips are from what we generally run on, let's start with GraphCore, top right corner. So it's like a UK-based hardware startup that designs semi-neuromorphic chips. So the architecture would imply putting more memory next to every single core. Memory is like a vague description. Like it can mean persistent memory, like SSD. It can mean RAM, VRAM. It can mean SRAM. I'm talking about SRAM specifically. So if you take an A100 GPU, it will have 40 or 80 gigabytes of VRAM, if I'm not mistaken, HBM2. And it will also have just 40 gigabytes of SRAM, 40 megabytes of SRAM. So like three orders of magnitude less memory. On the GraphCore chips, you will have 900 megabytes of SRAM memory available to all the, a chunk of it is available to each core. And that's given that the number of transistors and the size of the chip is roughly the same as the A100. But then there are like the colossal chips of the future, I would say. So like Cerebras, a US-based startup, they design what they call wafer scale computing. So they take the whole wafer, and instead of cutting it into smaller chips, they pack it into a single server that is as huge as half of the rack. So it's considerably taller than the DGX A100, which comes with 8 GPUs. But this thing only has one chip. And this chip boasts 2.6 trillion transistors compared to 60 billion in chips like the A100. So with CuPy, the transition would be as simple as just changing the import. So import CuPy as NP at the very top. And who can spot the only one other difference between this slide and this slide?
It's hard to see the code, by the way. Can you turn off the lights? Maybe the front lights?
You don't have to read it to spot it, to be honest. So Pearson correlation.
Input statement.
Again?
The input statement is different.
Oh, the import, yes. But aside from that, the function definition for Pearson correlation benchmark has 3 arguments in this implementation and just 2 arguments over here. And those are the kind of tiny, tricky little differences that will exist between different implementations of the packages, or may exist between different implementations of the packages. So with CuPy and NumPy, in both of those cases, there's like no universal rule as if every function has a D-type argument or if it doesn't. So oftentimes, when you do not provide this kind of argument, it will take all the inputs and will use the biggest scalar type that you provided as the scalar type of the output. Those kinds of differences you have to account for whenever you port your library. Port your application from one backend to another. Another notable thing, if by any chance you're doing any high-performance stuff or high-resolution stuff, there are differences in the way you cast integers or floats between different backends. And for those of us who have maybe like more computer science background, it will be entirely understandable. So even though there's like this single IEEE 754 standard for floating point operations, and even if your arithmetical logical units on the GPU and on the CPU implemented identically following the standard, whenever you have, let's say, a heterogeneous program, part of which will work on the CPU and part will be compiled for the GPU, they may not be compiled with exactly the same options. So you may have fast math flags enabled for the GPU code, and all of a sudden the math will become inaccurate and will not match whatever you had on the CPU predictions. Another notable thing is that oftentimes GPU drivers live with their own timeline. They have their own queue of operations. And this is true for CuPy. It's also true for Dask, even though it may not necessarily be about GPU backends of Dask. But those asynchronous frameworks, they may sometimes require you to put additional synchronization points in your source code, just making sure that whatever the work scheduled for the GPU execution up until this point has finished before you can proceed or, let's say, send the data back to the CPU to do the final post-processing. And very importantly, universal functions are not always universal. Another big lie. So universal functions are the freestanding functions. So essentially the ones defined globally in NumPy, not as member functions on matrices or tensors. So in NumPy, it's very convenient that you can provide native Python types such as lists as arguments to the universal functions. It may not necessarily be a NumPy array that you pass in. With high-performance packages, unfortunately, you may not have those freedoms. So a high-performance implementation would imply that you're working with very fixed, readable, and somewhat rigid, from Python's perspective, implementations of buffers and arrays. And this is an important thing to remember, and we'll come back to it. But before it, the big promise. Why are we doing all of it? And the answer is speed. Sometimes the boosts that we are getting are not really the ones that we expect. So just to clarify, every row here is a kind of operation that we had defined on previous slides. Every column is a different size of the input, meaning different sizes of matrices. The first column being a matrix with 512 by 512 floating point numbers as the most common content of your matrices. And the last column describes benchmarks for matrices that have 17,000 rows and 17,000 columns respectively. And I've color-coded some of the results. In worst-case scenario, your source may become slower. Yes, it happens. But very rarely, and you have to cherry-pick to find those cases when CuPy will actually do real bad. But sometimes you would get performance improvements at a factor of 1,000. And I'm not even saying compared to a baseline NumPy implementation. We took the fastest NumPy implementation, which is the MKL. We took the fastest CPU on the planet. We've liquid-cooled it. We've overclocked it. And we took the fastest available gaming GPU, which is not the fastest server GPU. And we've also overclocked it and took them head-to-head. Sometimes when it comes to arithmetical operations, if you have mixed precision enabled, you may not even get just boosts in matrix multiplications from the tensor cores available on the last 3 generations of NVIDIA GPUs, but you may also get the performance boosts in non-matrix multiplication operations just thanks to a couple of cool optimizations under the hood. So if it was just about the libraries or specific separate libraries, there would be very little to celebrate here. It would involve a lot of additional work for you just to go and find every separate solution, mix them together. But luckily, hardware vendors are uniting to help us. And I'm not really describing this ecosystem in full. So there's CuPy, cuDF, and cuGraph, which oftentimes have exact one-to-one mappings to libraries that are familiar to you. Sometimes they come with packages or, let's say, functions inside that you never expect in the original implementation. And my favorite example as a machine learning practitioner and natural language processing practitioner is that cuDF internally has functions for text tokenization. So for every library with a Q prefix, there is a library with NV prefix. So essentially, one of them would be, let's say, Python level wrapper, the ones that are with Q. And NV, standing for NVIDIA, is the underlying C library that makes all of the magic possible. So there is a library called NVText that comes with 3 GPU and hardware accelerated tokenizers that you can use for your natural language processing pipelines, which oftentimes includes models like BERT. And for byte pair encodings, for hashing tokenizers, you will have functions embedded into cuDF's underlying NVText package that you can call on your columns of strings. Cool thing to remember. But then there are also a few packages that I haven't mentioned here. One of them is cuSpatial, if you're doing any spatial reasoning. Another one is CLX. So whenever you work with data frames, there are also additional functions to convert string representations into some forms of scalars or, let's say, logical types specific for your application. We have date times like this in Pandas. But for some other applications, you may want to parse things such as IP addresses. And an IP address represented as a string, in worst case scenario, is 3 by 4, which is 12, plus 3, which is 15 characters. And we just encode it as a string. So an IPv4 address is just a 32-bit integer. Why not just work with it? So for all of that, and for cybersecurity applications, for kids who analyze a lot of different logs, and I know there's plenty of cybersecurity startups in Armenia, you could use CLX to parse your Pandas data frames of logs and prepare the data for machine learning pipeline and for detection and for fraud detection much faster. Another thing that is pretty popular on GitHub, but somehow I almost never see people using it, is QML, which implements some of the more classical machine learning tools, such as clustering algorithms like UMAP and TSNE. TSNE and UMAP are some of the most famous visualization tools and dimension reduction tools. Aside from those, there's also things such as ARIMA, autoregressive, what's the I4, I guess, integrated moving averages, or something along those lines. So it's very relevant for time series analysis. And then there is QX filter. So for the final end of your pipeline, when you want to visualize your stuff, it's not necessarily that you have to get your matplotlib, your plotly, or Dash. You can use QX filter to build up more performant dashboards with whatever is supplied by the rest of the ecosystem. And who notices ROC-M on this slide? Who knows what that stands for? Oh, there's a guy there. Do you know what that stands for? Great answer. I'm a bit too mouthful with every one of my descriptions. This is much shorter and more concise. So there is ROC-M or HIP, those like two abbreviations that you have to remember. And whenever you see those, things are going about AMD GPUs. So as every vendor is getting their discrete GPUs into the data center, and as this year we had our first exascale computer being officially unveiled and benchmarked for the top 500 of supercomputers, the Frontier in the Oak Ridge National Lab, this system is famously packed with like 10,000 servers with 4 GPUs in each one of them, which makes up for 40,000 GPUs, and all of them are AMD. How the hell are you going to program them? It's a bit complicated, especially if you're not doing some custom weather simulation software that you implement for one platform specifically. But with some of the ROC and HIP ports, and with a bit of additional work on the LLVM compiler, we'll be able to get a lot of this Python code and GPU acceleration to the AMD and Intel hardware quite soon. So as you see, results are becoming less and less uniform, in a sense that many packages may not have the implementation for the algorithm that we're interested in for, let's say, graph processing. So as the data, again, becomes less regular, there are less packages and less consistency between the implementations. Still, you may get 1,000 times performance improvements if you know what you're doing. But notably, Snap and iGraph do not provide the same interface as NetworkX. So here, a more fair comparison would have been RetworkX and cuGraph, as the interface is identical. Another important thing, I guess even more important than network processing for most of you guys, is working with really big tabular data sets. And we at Unum have a really fast database backend that we implement for our internal data management. And a good benchmark for this kind of thing would be the New York Taxi Rides data set. So it's, there is a very famous blog on the internet comparing all the SQL databases in terms of their speed of processing this data set. It's 2 billion rides from New York, shared by New York authorities by different taxi hailing platforms. And it implements just 4 queries. Generally, those are implemented in SQL in different dialects of databases. We re-implemented them with a Pandas interface. And just to make the benchmark repeatable on commodity hardware, not our servers and clusters, and in adequate amount of time, instead of taking the few hundreds of gigabytes worth of data that make up those 2 billion rows, we took small samples of it, and we put Modin, which is like native backend, and cuDF head-to-head. And unfortunately for Modin, at least today, the benchmarks were not very good. So for us, it didn't make much sense to use, let's say, Modin on the CPU backend. And I guess it's fair to say that Pandas interface is very complicated. It has too many functions. And whenever you're implementing a new library, a new backend with the same interface, it's very tough to get everything right from the very beginning. And sometimes when you miss up a function, this function will be then redirected to the original Pandas implementation. So if you're calling something in Modin that is not implemented, you are beneath triggering the Pandas implementation, not always knowingly. So when working with tables and with different sorting group by operations on the GPU side, we consistently would get, let's say, 10 to 50x performance improvements. The bad side here, again, GPU memory is very limited. Though luckily for you, if you are not really targeting for the top quintile of performance and your computer is not, let's say, $1 billion supercomputer, you can get away by using what is, let's say, today's or next-gen technology. So there's a lot of effort to bring unified memory into the ecosystem so that all of your chips would have the same address space for the data they store. And the driver beneath will do the smart work of, let's say, fetching and moving the data around so that if your data fits at least into RAM, it will be pulled in parts onto the GPU whenever it's needed there. So that's one easy, yet not the most performant way for you to scale to big data sets on the GPU. And just for the sake of completeness, there are a few other names I have to throw around for you to go and do your research at home. And you can write them down. My favorite out of those is probably NumPy. Definitely your Swiss Army knife for, let's say, easy optimizations and acceleration of your software. And importantly, I want to talk about, let's say, a few big problems with Python and how the ecosystem is partnering together to solve them. So Python's most common sequential type is a list. And even if we do not look into the underlying implementation in the CPython runtime, any person familiar with, let's say, linked list implementation would know that it's not really the most efficient form for enumeration, let alone the fact, there's no locality and you have to jump around. It's even worse when you understand that you're working with integers and the integers are packed into some variable length representation. So Python, out of all the languages that I've used, I guess, is the only one that doesn't have fixed length integer representation. Another big problem, as I mentioned, not using the ability to convert to enum types. So moving from strings to categories and then parsing date times as integers before starting to use them. And another thing to note, again, so if we had those lists, and lists are horrible, why not we make the next step and make continuous memory layouts? So there was a lot of effort to go there. And when choosing your algorithm in the future, make sure you understand your data layout. So is it sparse, is it dense, is it a matrix, or let's say adjacency list? But people had tried to solve all of it. So we'll talk very little about developing software, and we'll focus on developing intuition. But developing software, it's important to note that there is this PEP standard, Python Enhancement Proposal 3118, which defines a C struct that we developers can use to exchange information about tensors of various rank between number crunching packages. You have to just implement this to be able to provide tensors from one runtime to another. And the same for columnar representations. So Apache Arrow is the new big family of standards that pulled inside the Parquet set of formats. Feather has now become Apache Arrow IPC2 standard. And this is a new form of data frames, essentially. So just to note, this would allow you to send data from one place to another without needing to convert it every time you switch a package. So developing the intuition, I would recommend you to use maybe native Python types for very tiny sequences. Anything bigger would probably boil down to NumPy. Multi-threaded and hardware-accelerated CPU libraries are only meaningful if you're working with elements that are, let's say, in tens of thousands. And whenever you want, you can pack your native implementation with PyBind, NanoBind, Boost Python, or Swig. And then another thing is the GPU libraries. So all of that we covered, but is there more? So we work with data sets that are tens of terabytes, or let's say want to work with data sets that are hundreds of terabytes on every single machine. How? Let's taste the future and see what's about to come to the ecosystem of Python data science libraries. So you have all those pieces in your modern computer, like a CPU, SSD, NIC, GPU, and RAM. all of them used to talk to each other through the CPU, exchanging the data through one link. And this link is wide, but not wide enough to accommodate for modern data transmission rates. Luckily, aside from, let's say, Apache Arrow or that PEP standard, there is more happening in the ecosystem lower in the hardware level. So, or let's say at the driver level. So at the driver level, there is a standard by NVIDIA for the GPU direct storage for sending the data from from SSD onto the GPU, bypassing the CPU entirely. For bridging the device or the chips within the same server together in the same address space, there are a lot of unified addressing technologies and efforts implemented. For being able to share RAM as one continuous block, or let's say continuously addressable block between not one machine but many machines, there's remote direct memory access, which you more often see as RDMA, so it may sound familiar. And then there is also NVMe over Fabric. We want to use all those technologies to bring two very complicated worlds together. The world of working with very big data sets that are hundreds of terabytes, and GPU acceleration, where the memory bandwidth of VRAM is, let's say, 1.5 terabytes per second on every chip. So by doing all of it, imagine having Common Crawl, which is the biggest publicly available data set on the planet right now, the one that is famously used to train some of the biggest generative and non-just generative language models. But generally, it's not even used entirely. People use different samples of it. We want to be able to process this entire data set on just 2 machines in a matter of 20 minutes without any additional indexing. So for those of you who will want to go down the road of understanding all of this complexity of designing something like this, not just using, there are a lot of problems in designing a parallel algorithm. I famously used to ask kids on interviews who never programmed on GPUs on how to implement a parallel reduction when you have 10,000 cores under your disposal. But the same kind, or like very different but still challenging things, are external memory algorithms. How do you sort the data when you cannot just jump around and swap things together like with quicksort? As with any kind of benchmark like this or any kind of challenge, there's a consortium of people on the internet who love weird stuff. And there is a benchmark even for external memory algorithms that you can go and look into. And you would immediately see that even the algorithms that are implemented there are very different from the algorithms that you're studying in your CS class. So the hope is what we developed. So we have a hybrid transaction analytical processing tool that hopefully will do both the low latency operations, like the write transactions, and the read-intensive operations as the analytics for you, and will bridge together with the rest of the ecosystem. So as there was this BLAS, with a linear algebra standard that was designed like 40 years ago, we want to design similar standard for create, read, update, and delete operations in your data processing pipeline with just a very narrow C layer in between, and a lot of libraries growing out of it for the high-level interfaces, and a lot of different logic implemented beneath for you to be able to use. It's entirely open source. You can check it on GitHub. And the cool thing is in the bottom left corner here, UnumDB persistent ACID store. It's the first engine, database engine, with GPU acceleration support ever designed, and by far the fastest out of those who have CPU acceleration with SIMD instructions on 3 generations of x86 CPUs and on ARM CPUs as well. So with all of it, you can look into it online. I've mentioned a few potential usages for this kind of system, especially if you have, let's say, data transmission intensive application, like a recommender system that would often have a different trade-off between I/O and the amount of compute. We'll also be we are very excited to learn about your use cases so we can adjust for them and prepare data loaders and stuff like that for PyTorch and TensorFlow. So that's it. Check out UKV, check out Unum, and feel free to ask me any questions you have.
Okay, everyone, now it's time for questions.
Yes?
First of all, I'll wait for the mic now. All right. Thank you for your presentation. It was quite interesting. The processors right now are deterministic. They are not probabilistic, so they only give zeros and ones. And we are calculating like probabilistic answers. It's like in a core, it doesn't matter if the answer is like 99.99999% or 99.9998%. So I know there are new types of processors that don't divide between zeros and ones. So in a core, I don't remember quite the name of them. I was trying to Google. But in atomic level, the wall between 0 and 1 isn't divided like strictly. So the electrons can flow between the 0 and 1, and it gives a probabilistic answer, like a probabilistic value. So these kind of chips are being developed and are being used to calculate some machine learning tasks on a probabilistic level. I can't remember the name of those chips. Have you heard about this? And what is your answer? What is your comment on this?
So I do not know which one specifically you want to reference, but there's this amazing branch of analogous computing. So as there's binary logic and like all the algorithms that we design for it, there's also analogous computing, which yes, has a very probabilistic nature to it, in that you are not really defining your program. You define your program, but it's more of a form of simulation, and you let the computer naturally unfold the simulation to give you the answer. So it's a very different programming model, and the results would also be very different. So,
are there libraries being developed on these things, on these machines?
There are a couple of answers here. So there are a lot of algorithms designed for digital computers to simulate the expected behavior of an analogous system. So an example would be frameworks for simulations of quantum computation. But quantum computing is not the only form. So like, there's a lot of effort happening in optical computing space, and that's not the only one either. Hopefully that answers the question.
Yeah, thanks for the great presentation. Actually, the question is related to the graphs and BLAS. I saw that you have such rigorous benchmarks related to the CUDA, etc. I wonder if you have done such fork related to the graph BLAS. If you have any insights, benchmark related to it, and if you can share that, I'll be very grateful. Thanks.
Yes, sure. Great question. Thank you very much. Didn't expect that one. So for context, graph BLAS is a different kind of package. So it also implements the BLAS operations. But they are parameterized over the ring on which the arithmetics are carried. So instead of just like doing, let's say, the dot product matrix multiplication, you would use something like a tropical semi-ring with, let's say, minimum and maximum operations, and then all of a sudden the matrix product of two adjacency matrices, matrix product of an adjacency matrix of a graph with itself will give you the implementation of the Floyd-Warshall algorithm for all shortest path problem on graphs. Very cool bridge between, let's say, an implementation and the above logic for the discrete structure. In terms of possible implementations, there's a library called cuTLAS, which is a C++ template library for CUDA GPUs. It's templated, so I'm pretty sure it can be parameterized. But internally at UNO, we have our own graph BLAS implementation with both CPU and GPU backends. And I'm not 100% sure as of now. We're definitely slow on CPU, so we're significantly slower than MKL. But we might be the fastest on the GPU right now. And the difference between the GPU and the CPU implementation would be absolutely staggering. Like, if you have a GPU, go use it.